All right, yeah, well, welcome everyone. So we're on to the last chapter of the course, chapter 10, which is coping with NP completeness. I guess a few just quick organizational notes. So the assignment 6 is due next Tuesday. The final exam is the following Monday, right? So it's a pretty quick turnaround between the last day of class and the final exam. I will post I'll post a final exam from the last time I taught the course when it was an in-person final exam, so I think for the midterm, right, like it went online in 2020. So I was able to post the midterm from 2020, but I won't post the final from 2020 because it was like a 4-hour, or like you had 4 hours in which to complete it. So I'll post the final from 2018. It won't have any solutions, just I don't have written up solutions to provide you for that. But I'll also post, I have like a set of just questions I've kind of collected from previous finals along with solutions that I'll post as well. So it's not like a full final exam, but it's a set of questions where you can get some more practice on the different parts. So those will be the two things I'll post. I'll probably do that this week. And then I guess we should be able to, we'll get assignment 5 back to you before the final, but we probably won't get a graded assignment 6 back before the final because it's only 6 days, right? It's hard to turn around 150 assignments that quick. So anyway, that'll get updated on Learn. You know, like I'll post the assignment average where it'll give you the best 5 of 6, your score, and like you can check it at some point. You know, when I'll release that as soon as I have that graded. But I think that's about it. We'll be using these 4 classrooms. We actually have 4 assigned for the final. I'm not sure if we'll use the seating of all 4. So seat assignments will be like released on Odyssey, just like with the midterm. And at that point, you can check to see which room you're in, whether we're using all 4 or just 3. It just becomes a huge logistical thing if we use all 4 because it has to be at least 2 proctors in each room. So that means you need at least 8 people, right? And like have to, anyway, that'll get updated once I've got it figured out. Any other questions just on like the final or any administrative aspects? Yeah. You say you think the best 5? Yes, best 5 of 6. Yeah, and you don't have to turn. It doesn't matter if you turned in or not. I'll just take, I put zeros in the place of places that weren't turned in, and then just take best 5 of 6, right? So, and they're all out of 40. So that the only exception, right, is this last assignment's out of 45. Well, it's out of 40, but you can get up to 45 points. And I'll actually like carry that into your assignment average. So if you got 45 out of 40, and then on one other assignment you got a 35 out of 40, right? They would compensate for one another. Okay, so this last section is just, we've now talked about these hard problems, right? And that they're plentiful, essentially. There's lots of hard problems in the world, but we still have to try to solve them. Solving them exactly, we know that unless P equals NP, there's not going to be a polynomial time algorithm that exactly solves the problems. So now we have to look at ways to kind of approximately solve these problems, or to try and find the optimal solution like as fast as we can, accepting that it is likely going to take exponential time. And so we won't be able to scale to really large inputs. So this section is just going to give us a glimpse into this. And we're going to talk about 3 ways we can go about solving NP complete or the optimization version of NP complete problems. So one which is for search problems, well, within this class is intelligent exhaustive search. So basically we still try to find the optimal solution, but we're trying to do it in an efficient manner where we don't necessarily have to loop through every possible solution, right? You can imagine, like, for example, take SAT, and let's say there's 10 variables. One possible way to solve it would just be try out all 2 to the 10 possible solutions, right? True, false for every variable. So there's 2 assignments per variable. It's 2 to the 10 options. Just loop through them all. That will work. It just runs in exponential time. So intelligent exhaustive search is that we still ensure we've inspected every solution, but sometimes by inspecting one solution, we can eliminate from consideration related solutions. So for example, if we find out the assignment of x1 to false just won't work, we don't have to search any solution that contains x1 equals false. So this can be achieved through something called backtracking. And then branch and bound is the same idea, but where we're considering optimization problems instead of search problems. So here the runtime is exponential, but we still find the optimal solution. The other two ideas are ones where we give up on optimality. So in approximation algorithms, we have a polynomial time algorithm, and we are able to get a guarantee that says that it's no further than some known constant from the optimal. This is typically a ratio. So for example, in a two-factor approximation algorithm, it'll be an algorithm that runs in polynomial time and always returns a solution whose value is no more than twice that of the optimal value. So if the optimal TSP tour is 1,000, then you're guaranteed to never find one that's more than 2,000. This is what an approximation algorithm does. And we actually kind of gave an approximation algorithm for set cover, if you remember. It was a log n approximation. So it wasn't even a constant factor, but I always found one that used no more than log n more sets than the optimal solution. And then the third one is, so the problem with approximation algorithms, or not problem, but the difficulty in it is that you actually have to establish this bound of how well you do relative to optimal. What's often done in practice is just to use what we call heuristics, which are ways that we hope find good solutions, but we have no guarantee that they actually find good solutions. So it's just, I mean, there are courses, you think even in an undergraduate curriculum here, that are basically on heuristics, right? The like intelligent systems, like 457 A, B, these courses are basically courses on heuristics for the most part, right? It's just like different ways that people have come up to solve these hard problems approximately with no guarantee that they actually find a solution close to optimal, but with some evidence that they work well in practice. We're only going to very briefly talk about a kind of more principled one that's called local search, where basically we find solutions and then try to find neighboring solutions that have better value and keep moving to neighbors until we can't find a neighbor that has better value. And that's kind of the same idea we used in linear programming, but there we were able to guarantee it was optimal, right? So let's begin with the idea of intelligent exhaustive search. And so we'll begin with backtracking, which applies to search problems. And we can consider SAT as our example. So let me write out a SAT formula, and I'm just going to show you what backtracking looks like by example, because I think it really illustrates the idea. So I'm going to write out a fairly big SAT formula in conjunctive normal form. It says phi is W or X or Y or Z, and W or, oops, not X, and X or not Y, and Y or not Z, and Z or not W, and not W or not Z. Okay, pretty long, but let's say that's our formula. So what we do is we're going to construct a search tree where we're basically searching through assignments of the variables. So this has the variables X, Y, Z, W, right? 4 variables. And so it's actually not that big, right? You could really just do the brute force search over all possible solutions and find one. But this is just to illustrate the idea. So we start off at the top of our tree with the entire formula. Yeah. Or yeah, thank you. Yeah, totally. Or here, yeah. Okay, so we start off, we pick a variable, and we branch. One where we set it to false and one where we set it to true. And then we plug in that assignment into the clauses. We know if that literal appears in the clause, then we've already satisfied the clause, right? Because with the ors, we just have to set one literal to true. And so we can kind of shrink the formula, and then what's going to appear in a node further down the tree is what formula is left over after I've set, let's say, W to false or W to true or whatever. So I'm going to start by branching on W. And it's going to be a kind of big tree, so I'll go off like this. So let's first say we set W to true. Then the first clause is satisfied, right? Because W appears in it. Second clause is satisfied, W appears in it. Third, fourth are not satisfied. The fifth one has a not W. So that's false, right? If we set W to true, then not W is false. So the fifth one just becomes Z. And the sixth clause, the very last one on the end, it has not W or not Z. So it just becomes not Z, right? Because the W part is false. So what we're left over with is, it's already shrunk quite a lot. We get X or right, first two clauses are gone. X or not Y, and Y or not Z, and Z and not Z. Going the other way, if we set it to false, it just drops out of the first clause. So this side is actually going to be longer, but we have X or Y or Z, and we set W to false, so that becomes not X. And the next clause is satisfied, X or, I'm looking at this clause here, that clause is satisfied. Sorry, why am I saying that? That clause is not satisfied. That clause is X or not Y. And Y, I'm now looking at this clause here, Y or not Z. And then the last two clauses are satisfied. That's what I was thinking about, right? Because I've got a not W here, so that's true, and I've got a not W here. So this is my W equals false branch. Now, all I do is I keep branching. One thing that actually, can you see something about the right branch already? That, yeah. Exactly, yeah. There's no way to satisfy those last two clauses, right? Remember, I have to satisfy every clause. One clause says I have to set Z to true. The next clause says I have to set it to false. There's no way to do both. So I actually, in this example, I could stop branching on the right-hand side. I've already kind of arrived at a contradiction. So there's no way that a solution can have W is true in it. I really only have to go down on this side of my tree. So I'm just going to write this can't be satisfied because of this. No need to expand further. So I can just go down on the left-hand side and I pick a variable and branch on both sides. I'm going to pick Y. So let's take the Y is true side and then the Y is false side. When Y is true, the first clause gets satisfied. That clause is satisfied. For that clause, I get that X has to be true because this part's not satisfied, right? And the last clause is satisfied. So I'm just left with these two middle ones, and it's going to be X bar and X. Right, so what's left here is X bar oh, X bar, not X hat. Sorry. That's again going to be one I can't expand any further, right? I've arrived at a contradiction at that clause already. And then on the false side, the first clause becomes X or Z and X bar. And then the next clause is satisfied. And the last clause I get and Z bar. So this I'm just going to say expands to false because there's no way to do it, right? And I'll actually write that here as well. False. And now I just have to expand this clause one more time. Let's say I pick Z. Oops. Sorry, I was using true or false. True. Z equals false. So the true side doesn't work because I've got not Z here, so that evaluates to false. And yeah, and on the false side, I satisfy the first clause, but I'm left with X or not X, or X and not X, sorry. Yeah. Oh, yeah, sorry, I messed up here, right? So this is satisfied. Oh, did I make a typo here? Yeah, sorry. Yeah, if you look here, right, it's X or Y or Z. And then I set Y to false. So this should not have a bar on top. Thanks. Right, yeah. And so the thing we can see, right, this example is a little bit long, is that we get there no satisfying truth assignment. Right, every branch ends in a false. And if you look to do it, we didn't have to search over all 2 to the 4, which is 16 possible assignments, right? We only expanded W, Y, and then Z. And so, you know, we were able to trim several of these branches and over on the right-hand side. And this can become quite meaningful when the problem gets big. And so that's really the whole idea of backtracking. I'm writing it for SAT, but more or less what I do is I start with like my full problem. I make a sort of assignment of some sort. I then do a test. My test is like, is it possible to satisfy the clause that remains? I get a yes, a no, or I don't know kind of thing, right? Like a yes would mean I found a satisfying truth assignment. A no would mean I've arrived at a contradiction, like what happened on the right-hand branch. And I don't know means like one of these ones, right? I'm not sure yet. I have to keep expanding. And then I just keep expanding the ones that I have that I'm not sure yet until I hit one where I get, yes, I've found a satisfying truth assignment. So let me like formalize that idea. So just to give a bit on the structure. So each vertex is a smaller SAT problem, which we call a subproblem. When you reach a false on a particular branch, then you prune the search space That doesn't need to be there. And there's no need to explore farther on that branch. So backtracking looks like this. Start with a problem, which might be the full problem in the case of SAT, or I'll give you another example where it's like the input, essentially. And let's set S to be the set of active subproblems. And then while we have active subproblems, so active nodes in that search tree, we choose a subproblem. That's going to be the one that we're going to expand next. We expand it into smaller subproblems. So that's in SAT, that's pick a variable and expand it by setting that variable to true or false. We generate two new subproblems. And for each new subproblem that you get, you do your test. So if the test succeeds, that means we've found a satisfying truth assignment in the case of SAT, and we just return. If the test fails, then that can't be part of a solution, and we can just discard that subproblem. We don't have to expand it any further. And otherwise, we add that subproblem to our set of active subproblems, and we continue. And if our set of subproblems becomes empty, and we haven't yet returned on line 7, then we can report that no solution exists. We've exhaustively gone through every solution. So it's actually not too bad to implement such an idea, right? Because I'm not really having to maintain the tree or anything. I just have to fill in these ideas for what's choose, what's expand, and what's test. So let's just do it for SAT. I mean, I already explained it, but so for choose, it's pick. We're trying to choose which subproblem to expand next. So choose so what you could do is you could choose the one to expand next. Let's say the one that has the fewest clauses, or the one that has the smallest clause, like the clause that has the fewest literals in it. Either would be valid things. That contains fewest clauses to expand next. Or you could do the smallest clause, because maybe that will lead you to a fail quicker, where you can stop expanding the branch. Now to expand, that was easy, right? I just pick a variable. Again, we have a choice of variable, and maybe you could think about like, what's the best variable to pick? Maybe one that appears in a lot of clauses. Pick a variable, and then you get two subproblems, right? One where you've set it to true and one where you've set it to false. So expand using a variable in that clause, maybe. Let's say the smallest clause. Maybe I'll just say in a clause. And that creates two new subproblems. And then we do the test. So test, in the most basic test, we would just have it succeeds if no clauses. Remain, because at that point we've satisfied all the clauses. It fails if there is a false clause or the pair maybe X and not X. Right? In both those cases, we declared that it was a failed subproblem that couldn't lead to a solution. And that's it. I mean, so you can see there's some design choices in like doing a good job of this. In particular, you can change the runtime of this a lot by like optimizing your choose mechanism and optimizing your expand mechanism. Like which variable should I use to branch next? Which one will cut down the search space the most? And so those are kind of heuristics, right? Like how I do the choose and how I do the expand, but they're heuristics within this principled idea that actually at the end of it, I am going to find the optimal solution. The solution. All I'm trying to do is do it as fast as I can. And so I can use heuristics to hopefully search the space faster, but it won't affect the correctness of the algorithm. So in the worst case, this runtime is still exponential, but it works quite well in practice. And so let me give you another example, which is Sudoku, which is the last question on assignment 6. So most of you familiar with the Sudoku puzzles? You've seen these things? Yeah. You're given a 9x9 grid. It's separated into 9 3x3 subgrids. And you have to enter, and there are some numbers that already appear in the grid, right? In the 9x9 grid, there are numbers 1 through 9. And your objective is to fill in the rest of the grid squares such that each subgrid, 3x3 subgrid, each row in each column contains exactly one of each number 1 through 9. Or in other words, contains no repeated numbers. So the 9x9 grid is divided into 9 subgrids. Each square can contain an integer from 1 to 9. You're given a partially filled grid, and you want to fill in each square such that each row, column, and subgrid contains no repeated numbers, i.e. contains one of each value from 1 to 9. Or determine no solution exists. Although I think in like a Sudoku puzzle, they never give you one where no solution exists, right? I don't think, I've never seen that, but. So how could we frame this in the backtracking idea? You can see here, right, for Sudoku, it's not probably going to be feasible to just test every candidate solution, like exhaustively. I mean, the most naive exhaustive way would be just for every single cell, you have 9 possibilities. So you have the number of empty cells. I don't know how many they filled in. Let's say they filled in a third of them. So you've got like 2/3 of 81. And you have 9 possibilities for each of them. So it's going to be 9 to the power of like 25 or something possible completions of the grid. You would check each one and then discard if it's not a valid one, right? That seems like it's not going to work. But with backtracking, if you have time and you do that assignment question, you can solve like any problem that's online like very quickly, in under a second kind of thing with backtracking. It's very effective. So I'll give you a sketch of just how we do it, which basically you just expand on this a little bit, and that's the written part that you submit for the assignment question. So this is, and then up to you whether you do the implementation. So first, P naught in this case is just going to be the input, the initial grid. Now we have to choose, right? So you're trying to choose a subproblem to expand. Initially, the only one you can expand is P naught, right? But in general, I'm going to have a set of active subproblems, which will be partially filled grids, and I want to decide which one to expand next. So simple idea might be it's often a good idea in backtracking to try and go deep, right? Try and go towards a solution. And then the idea of backtracking is if that didn't work out, I come back up and I try and go down another branch. So maybe I try and fill in the one that I've already got the most filled in for, right? The one that's closest to a solution, I try and fill in another square for it. So choose the grid. That has the most filled in squares. Now for expand, I have to choose a cell in that grid. And I create a subproblem for every valid assignment for that. I mean, basically, initially I create 9 subproblems, right? I enter every number 1 through 9. And then I have a test. The test is like, does every row, column, does any row, column, or subgrid have a repeated entry? If it does, I can immediately discard. Otherwise, I add that to my set of active subproblems. So pick an empty cell in my grid and create 9 subproblems. P1, P2, up to P9. One idea here is to pick the cell that's most constrained. Right, like if that cell already has, you know, in its row, column, and subgrid, there's already a lot of numbers, then there's few options for that. That's kind of what we do, I think, when you try to solve it yourself. So that might be a good idea where you can go deep quickly and get to good solutions. But up, you know, that's a design choice. And then for test, check if the subproblem, or I guess the grid, I'll say, has a repeated entry in any row, column, or subgrid. If yes, then it can't be part of a solution. So I can say fail. If no, add. Well, I guess there's 2 options, right? If no and the grid is filled in, then return. So if no and grid is complete, then return. Else, I'll write the else underneath and. So if no, but the grid is not complete, then just add to my subproblems. And that's it. I mean, that's the basic idea. So the way that like you would go about this really is don't try to be too fancy with it. You just literally, each subproblem, you just generate, make some data structure to store your 9x9 grid. And just each time just create a copy of it, right? And that's your set of active subproblems. It might get pretty big, your set of active subproblems, but it should work reasonably well. Don't try to like optimize where you say, okay, this grid came from this other grid, so I'm only going to record the difference between my new grid and the one it came from, and then keep a pointer to the parent, or like it's getting too complicated. You shouldn't need to do that to get something working. You just, you know, when you branch, just create 9 copies of the grid essentially, check each one, discard them if they don't work. And I mean, that should be enough to sort of get something working. Just take the bare bones idea of backtracking. Okay. So many tweaks to improve performance, but this is the basic backtracking framework. And it's quite powerful. Like, I mean, I've only given 2 examples, but it's used in a lot of areas. So the extension of this is backtracking, as I've described, is only for search problems, right? At the end, it returns solution found, Sudoku complete, or no, it doesn't optimize an objective function. When we want to try and optimize an objective function, we can use something related, which is called branch and bound. So that's what we'll talk about next, but why don't we take a 5-minute break and then we'll continue. Okay. So in backtracking, the test idea was pretty clear because basically we test, could this be a solution? Yes, no, right? Yes, no. Yeah, okay. I guess it's yes, no, and then there's a special case where it already is a solution. Then for sure, yes, right? Then, but basically, we're just saying yes, it could be a solution, or no, it couldn't be. If we're thinking of an optimization problem, what we're trying to ask is, could this be part of an optimal solution? Right? You've got like a partial solution to the problem. Like you've partially packed your knapsack or something, and you're asking, could this be part of an optimal solution? And so you need to kind of change your idea a little bit. For right now, we'll just consider minimization problems, but it's the same thing for maximization, just the terminology, really. But instead of testing a problem for failure, we want to discard a problem when we're sure that it leads to a solution with higher cost than one that we've already found. You know, initially we don't know what the optimal solution, what the cost is going to be. So we really have to wait until we find a solution, and then that's our benchmark, right? Now we find new solutions and we say, could, or new partial solutions, and we say, could this be doing better than the one we've already found? If it still is possible, we could do better with it, we have to keep it. If we can be sure, there's no way, right? Like for example, if it already costs more than the best one I've found, that's an easy way to discard it. But maybe we can do it a bit more intelligently than that and trim the space in that way. So it starts off the same. We start off with a subproblem or with a problem, and we have our active set S, and we have a best so far cost, which because it's a minimization problem, we set the best so far to infinity initially. And while we have problems in our set, our active set, we choose one, remove it, we expand exactly the same, and then we loop through all of those subproblems we just generated. We run a test on it, and our test says, one, if it's a complete solution already and it has a better cost than best so far, then update best so far. Right? We just found a better solution. Otherwise, we check if a lower bound on the best cost you could get using PI as part of the solution, if that is better than best so far, then we have to keep it. But if our lower bound on the best solution containing PI is already exceeds best so far, then we know there's no way to get a better solution using PI. And so we could discard it. So else, if the lower bound is better than best so far, then we add it to PI or add it to S. So I think we need to be a little bit more concrete here about like what we mean. And of course, this whole idea, the power of it hinges on what we do in lower bound. So choose and expand are just as before. Lower bound, the idea of it is that it should be something that's fairly quick to compute because we're going to generate a ton of subproblems in our search typically. So you want a quick lower bound on the cost of any solution that includes PI. So what's going to happen in this backtrack or a branch and bound idea is we first go deep basically in our search tree, just get to a solution. That gives us a benchmark, best so far, that now we can kind of go back and start trying to find other solutions and determine, could this other partial solution lead us to something better than best so far? Yes or no, right? And if it could, we keep expanding it. If we can conclude that it can't, then we can discard it and all of its children, right? Everything that goes down from that further. So let's consider an optimization problem now that we're going to try and implement, or like I'll give you a sketch of how a branch and bound would work. And we'll take the traveling salesman problem because it's a simple example. So this would be a bit difficult to like come up with on your own. So I'm going to like just give you some of the pieces. Like, first of all, it might not even be clear, like what's a sub problem? I'm going to say that a sub problem is just a sequence. It's like a path in the graph. You know, of it could be just 2 vertices in a row, it could be 5 in a row, something like that. And then when I'm asking, like, could that lead to a better solution? It's like, take any tour that uses that path as part of its solution. Right? So it's going to be useful. So we define our subproblem as a path starting at some vertex A, passing through some vertices S, and ending at B. So it's going to take the form of A, S, B. Where it's just useful, we say that A and B are in S. So S is all the ones that are on this path, and then A and B just record what are the endpoints of that path. So I don't know, let's say this is my graph, then maybe this could be a subproblem, and S would be, oops, thinner one. S would be these 3 vertices here. Right, so it's just a chunk of my tour. So now what I'm going to do, right, to construct a TSP tour is basically grow a path. It's like, to expand this path, I should add another vertex to its end, like, you know, to go after B. So you could think in this particular example, after B, what could go next? Well, that could go next, or that could go next, I guess, right? Either of those 2 ones on the right. So at each step in branch and bound, we extend a possible solution by a single edge, B to X, where X hasn't been visited yet. Okay, so this leads to a new subproblem. Which would look like A, now we go S and X, and then it ends now at X. And so in total, there's V minus S vertices X that could go next. And so we would get that many subproblems, right? There's when I expand a given subproblem. Okay, and maybe the one other thing I'll say is, like, when we record ASB, we'll say that that's the cheapest, like that records the best tour or best path that goes from A to B passing through S. Right, so it's like the best one, because there's no point keeping a another one of higher cost that does the same thing. So. Okay, maybe I'll just write that here. So cheapest path starting at A, passing through S, ending at B. Okay, so now when we expand a subproblem, we get a bunch of new subproblems, which look like A, S union X1, ending at X1, A, X2, and so on. And so the key thing, which will kind of always be the key thing in these branch and bound algorithms, is trying to figure out what's a lower bound. So if I have this path in the graph, how do I lower bound the best tour that could use that path? You know, the cost of the best tour using that path must be at least this much. That's what I'm trying to be able to say. And so it should be like the cost of the completing tour, right? The tour that leaves B, goes through all the other vertices and comes back to A. My search isn't going to be fast if I have to optimally solve that, because now like I'm having to solve TSP basically every time just to decide whether to keep a subproblem. So that's why I want something that's cheap to do here. And the idea, there's a bunch of different ways that this can be done, and there's like really neat things people have proposed. I'll give you one idea that, so, okay, maybe can someone give me a valid lower bound that's like the most naive thing you could possibly do, but that definitely would work? Yeah? Yeah, okay. So what was said was the cost of the minimum path, the cost of the path from A to B, right? The thing that I already have, plus, and then something about like the minimum edges in the rest of this, you know, the part I haven't visited. I mean, I'm going to say like an even more naive one is, what if I just use the cost from A to B and I say the rest of it's going to cost me 0? That's definitely a lower bound. You agree? It's not going to help me discard much though, right? Like we'd like to do better than that. But that would be a valid lower bound. And you could then just implement backtrack or branch and bound with that. But exactly like what you said is what we want to do. Something where we also take into consideration what would be the cheapest way to complete this. And so let me draw a picture to try and show you how this would work. So given a subproblem A, what is the lower bound? What is a lower bound on the shortest completing, or a subproblem ASB? What is a lower bound on the shortest completing tour? Let me draw an ASB. So let's say it starts here, A, maybe goes to there. Oh, how about like that? And so this is my S, and my current path looks like this, okay? And now I have some other stuff out there. So let's say I have, right, this is the rest of the graph. So my lower bound on the cost of the best tour that uses that chunk is going to be, well, 1. I'm going to take the length of ASB, right? Now, somehow I have to get from S to this cloud, right? Which is all the stuff I haven't yet visited, V minus S. And so my idea is going to be take the cheapest edge that takes me from S to, or takes me from A to all the ones out there. Take the cheapest edge that takes me from B to the ones out there. And then take the minimum spanning tree of all these ones of V minus S. And I claim that's a lower bound on the tour. So let me draw it and then see if you agree or are convinced. So this stuff out here, this is V minus S, right? It's everything that's not in S. So 2, I'm going to do the shortest edge from A to V minus S. 3, shortest edge from B to V minus S. And 4, the MST of V minus S. How about I pick another color and draw these things? So what's, assuming the lengths are just the like Euclidean distance on the page, then the shortest edge from A to S, or A to V minus S, has got to be this one here, right? From B, I guess it's, should I pick a different color? I don't know. I'll use the same color. This one here. And then what's the TSP look like on, or sorry, the minimum spanning tree look like on V minus S? I think it's something like, I guess the shortest edge we'll use, just add the shortest edge that doesn't create a cycle. So I guess it's that maybe. And I think that one. Then, I don't know, that one maybe. And then that. So this part's the MST. Shortest edge from B to V minus S, and this is shortest edge from A to V minus S. Yeah. Like why to this one? Oh, so I make a tour or something, or? Yes. So what I'm not actually going to worry that the set of edges I use is a tour. Okay. All I'm going to try and do is get a sequence of edges, and then I say whatever the sum of the costs of these edges are, it's got to cost me less than the TSP that uses the black part. And so you agree, like the TSP's got to use some edge to get from A out to this cloud, right? That edge is going to cost at least this much. It's got to use some edge to get from B out to the cloud. Again, that's going to cost at least this much. And then it's got to do, it has to visit all of these vertices in V minus S. A possible solution to that minimum spanning tree is a path, right? It either could return a path that by chance takes me from this endpoint to the other one, in which case, you know, I've found a tour, or it might return a tree, which costs even less than the best path, in which case, you know, it's got to be cheaper than the TSP. Yeah. Not even. All I'm trying to do is I'm just trying to say, any TSP or the TSP, the best TSP that uses the black must cost at least as much as the black edges plus the purple edges plus the orange edges. So I'm just trying to obtain a cost, a lower bound on the cost of the TSP that includes the black edges. Is that making sense? Isn't sort of? So TSP that uses ASB must cost at least as much as the sum of these edges. And so I guess you could ask, why, right? And I mean, I hope that picture kind of explains why, but I will just say, what's the best way to explain? So maybe I'll say it like this. So a path through V minus S is a spanning tree. Of V minus S. Oops. Therefore, the minimum spanning tree must be no longer than the path. So that's the argument that those orange edges must cost less than or equal to the path that in the TSP that visits, that uses the path ASB. Yeah. 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 But it's actually any path that, like, if you just thought of this cloud of vertices in V minus S and just say, what's the shortest path that visits all of them? Like, it can free endpoints. The cost of that path has to be greater than or equal to the minimum spanning tree, because that is a spanning tree. It's a candidate solution in the minimum spanning tree. Yeah.
So when we said AS,
yeah.
To find the
We're always going to be like building it incrementally, I guess. So we won't really, like, it's all going within this framework here. So we start off, well, I'll fill these details in, but I think it might become clear that we don't actually have to compute anything on ASB. Yeah. Yes. Yeah. Not the way I'm talking about. We can't, that question was like, do we have to recompute the MST each time we do this? So yeah, every test we want to do, we have to compute a new MST. So it's, costs us something to test a problem for sure, but it gives us a lower bound on the TSP tour that's actually quite informative, I guess I would say. Right? I mean, even looking at this, right? The cost like that, I mean, I just drew these dots arbitrarily, but the tour that we got looks not too far off from what the TSP would look like on those, right? I think actually the TSP would just do like what someone said. Instead, it would go from the one that A visits down to this one here, then back and across or something, right? Like you just rearrange this edge to go over to here. That would cost you slightly more than what's being drawn. Yep. You would then have a very good lower bound, but you've got a bunch of subproblems like in your active set, so you don't yet know. Like now you've got a tour, you can update best so far, basically. But yeah, you wouldn't have to further expand that particular subproblem, actually. Okay, so the branch and bound algorithm operates as follows. We pick a start vertex. Then our initial subproblem is just going to be that vertex. A, it only visits A and it ends at A. And we create now V minus 1 subproblems where we grow by one edge. So each of these subproblems now is just going to be going from A to X1, A to X2, A to X3, and so on. We compute a lower bound for each subproblem and add it to S. Then you choose one of the new subproblems to expand next. Typically, you choose the one with the smallest lower bound to expand. And once you complete a tour, you update best so far and drop all the subproblems that have a lower bound bigger than best so far because they can't lead to optimal solutions. And you just continue the search until S becomes empty. So, I mean, this is very much a crash course on like a kind of complicated idea in doing this branch and bound correctly, but I think it gives you some insight into how you can do a branch and bound type algorithm. And there are a bunch of other like ideas that people add into branch and bound algorithms to make them more efficient. Okay, maybe briefly we'll just do the introduction to. So that basically now we've covered intelligent exhaustive search, just these two ideas of backtracking and branch and bound, right? And now an alternative idea is approximation algorithms, where now we want to ensure our algorithm runs in a polynomial time, but we give up on optimality. And so consider a minimization or a maximization problem. And suppose we have an algorithm. And let's say that if I give it an instance I, it returns a solution with value, it shouldn't say values, but just value, AI. Right, so that's the cost that it returns. Then the approximation ratio of an algorithm, it depends whether we're doing a minimization or a maximization problem. If it's a minimization problem, then we take the ratio between the cost that the algorithm finds and the optimal cost and search over all possible instances and find the maximum possible ratio, right? That's going to be the maximum gap between in a minimization problem, right? The denominator is going to be smaller than the numerator. And so you find the instance where the ratio between what my algorithm finds and what the optimal is maximized. In a maximization problem, instead, now the denominator is bigger than the numerator, right? The denominator is the best value you can get. And so now you try and find the one where the numerator is minimum relative to the denominator, to the optimal. So opt here is the value of the optimal solution on the instance. So for a maximization problem, for a minimization problem, your approximation ratio will be a number greater than or equal to 1. For example, in TSP, a 2-factor approximation, right, would return a tour that's always no more than twice the length of the optimal tour. And for a maximization problem, it's going to be less than or equal to 1. So for example, in knapsack, if you had a 1/2 approximation for knapsack, you would always be able to pack your knapsack such that it contained at least half the value of the optimal solution. So I'm only, yeah, just like there's these two ideas, right? Maximization or minimization. And so if you have an alpha approximation for minimization problem, then that means that for all instances I, the value you get with your algorithm is less than or equal to alpha A times the optimal, like alpha, that approximation ratio you had times the optimal. And so then basically what you want to do in approximation algorithms is, given a problem, an optimization problem, usually one whose search version is NP complete, or the optimization problem is NP hard, your goal is to find the algorithm A with approximation ratio closest to 1. Right? Close to 1 is good for both minimization and maximization. It's just minimization, it's going to be a number bigger than 1, maximization, a number less than 1. And for it to be called an approximation algorithm, it has to run in polynomial time. So that's the idea. And there's actually a really interesting area in that there are, even though there are a bunch of optimization problems, right? All whose search version is NP complete. Some of them, there exist good approximation algorithms. And some of them, there do not exist good approximation algorithms. And you can actually prove that there aren't good approximation algorithms for some problems. So as an example, set cover, the one that we talked about, we found a log n approximation for it. And there is no better approximation algorithm unless p equals np. That's been proven. On the other hand, take TSP with where the edges satisfy the triangle inequality. We'll talk about that one. That one can be approximated to a factor of 2 using a really simple algorithm, and it can actually be approximated to 3/2 using a slightly fancier algorithm. And if you restrict yourself to Euclidean edge lengths, it can actually be approximated arbitrarily closely to optimal. And I'll talk just very briefly about this tomorrow, which is, it's called a polynomial time approximation scheme. So it's like these different problems, their search versions are all NP complete, but when it comes to optimization for approximation algorithms, some can be approximated very well and some not very well at all. If you take general TSP, there exists no constant factor approximation, and you can very easily prove that. I'll show you that tomorrow. Yeah.
So for this, we still have to calculate.
Yeah, but you don't have to, like, it'll be like what we did for, you can sometimes get the gap from optimal without actually knowing what optimal is. Kind of like what we did with set cover. So I'll show you this for TSP just because that's the one we did with branch and bound. But why don't we postpone that to tomorrow, because we don't have so much to cover, and we'll finish up this section tomorrow.